Okay, so welcome everybody again. It's my pleasure to welcome all you in this new January 2025 Discover Us webinar. Today we have a talk about the COLMENA project presented by Francesc Lordan. Francesc is the leader of the programming models for Novel Distributed Infrastructure Group at the Barcelona Supercomputing Center. His research focuses on programming models that aim to ease the development of parallel applications by hiding the technical concerns of heterogeneous and distributed infrastructures. Francesc is currently tackling the challenges of programming applications for novel distributed infrastructures, such as the digital continuum or swarms. Currently, Francesc leads the technical efforts for developing the meta-kernel layer in the frame of the EU Horizon Europe ICOS project, and he's also leading the COLMENA and HP2CDT national projects. So, Francesc, whenever you want.
Okay, thanks, Rosa, for the introduction, and welcome everybody. First of all, I would like to thank also the Discover Us organization to give us the chance to share the research of the COLMENA project that we are doing in the COLMENA project. So probably if you are already attending to this webinar, it's probably because you have already heard about this digital continuum, the motivation behind it and its benefits. But I would like to, I'm not going to lose time on that, but I would like to spend some time on focusing on the problems that we have seen in the digital continuum and that we think that are important, that there are mainly two big problems. And that are, one is the lack of programming environments for this digital continuum. At the end, when you are trying to develop a service deployed on digital continuum, usually these services are just a composition of many containerized subservices with a specific logic. And many of the, when you are developing this kind of services, you have to be expert in all these technologies that you have to integrate. And part of these technologies are also all the communications. So whenever you are trying to develop a service, you need to be an expert on many technologies. And at the end, you have also to be expert on the deployment that you want to use. You are having a static deployment where you're specifying these subservices needs to run on the edge, these subservices need to run on the IoT, these subservices run on the cloud. And at the end, the implementation of the whole system depends on, it's prioritizing the simplicity of this deployment. And this is one of the big issues that we have. It's the lack of programming environments that simplify the development of applications. On the other hand, the continuum management is something, it's a heavy problem, and it's a problem that normally it must be solved in a centralized way. This is because we have a large number of devices. These devices have a lot of heterogeneity. And in fact, you have a lot of dynamicity, both in the network and on the workload. So at the end, you need a lot of computing power to find out which is an optimal deployment strategy. And once you have found an optimal deployment strategy, you need to continuously check if that's the best strategy, given the dynamicity of the network and the workload. So at the end, you usually have this orchestration happening on the cloud. And you have your whole system, it's cloud-centric. And if you lose the connectivity to the cloud, you have a huge problem because the whole service is useless. So in that sense, what we propose to you as a solution, it's based on two parts. One part is a programming model offering programming models that is the coding and the integration of the different services that compose the service. And then for the continuum management, what we propose to have is this runtime system that decentralizes the orchestration of the application. And it's precisely there where the workflows and distributed team in workflows and distributed computing team of the BSc has expertise. This expertise has come for many years. We started with COMS more or less 20 years ago. COMS is a programming model that allows the converting into a workflow some sequential code. This is, for instance, a sequential code in Python. The only thing that we need to do is to select some of the methods inside this inside this example code, in this code, in the sequential code. And whenever I'm annotating it with this add task annotation, and whenever we have a call to this increment method, to this annotated method, it will be replaced by an asynchronous call, an asynchronous task. Then with a runtime system, it will detect all the dependencies between these different tasks and create a dependency graph like this one that we have in the rightmost part of the slide. And this task can be executed asynchronously on a distributed environment. One of the main benefits that COMS has is that additionally, it can adapt the workflow to the execution. And for that, we have this COMS wait on method that allows us to make a synchronization on the value and adapt the whole workflow to the specific execution of that application. Okay, and that simplifies a lot the definition of complex graphs like the one that we have in the slide. Otherwise, I mean, other systems allows you to describe some workflows manually, and that if you have to, that doesn't scale if you have many tasks. So at the end, besides the programming model, we also have a runtime that while the application is executing, it creates this dependency graph, as I mentioned, and all the tasks that are dependency-free, they can be submitted to different resources that we can use in the infrastructure, like for instance, PMs or other nodes in the cluster. Whenever a task is completed, then we can release all the dependencies and release synchronizations and launch new tasks executions. So this is a little bit the original programming model that we had in the workflows and distributed systems. And it was targeting mostly clusters and clouds, where mostly we have an infrastructure that's quite static. It's stable unless you have some scalability or auto-scaling things that usually are under control. And you are normally executing in one single node, one execution of one workflow. And this matches perfectly with a deployment, with a master worker strategy for the deployment, where you have one node generating all this workflow and orchestrating the execution over a set of workers. When we are running on the cloud edge IoT environment, we are including in the infrastructure not only these static nodes, but also we are including mobile devices. And with that, we have a highly dynamic and out of control infrastructure that sometimes you have a new mobile connecting into the system or a mobile leaves the system, and that may bring some troubles to the orchestration of this, to the execution. In addition, we don't have one single point of execution. We're not just executing one workflow. At the end, all the nodes may require to launch some execution, probably some execution request can, I mean, in fact, you can have several multiple execution requests at the same time. So that means that you have to orchestrate the execution of several workflows simultaneously. So this master work deployment strategy is no longer valid. So what we thought is that we need to have some peer-to-peer system where every peer is generating its own workflows, and the orchestration of the tasks, it's a shared responsibility. So a little bit, with that idea, we had this colony framework that was extending the COMS programming model to offer a workflow as a service interface where anyone can connect and request the execution of a workflow. This agent would squeeze the embedded devices, computing devices, in the same node to get the most performant execution of that workflow, parallelizing it and storing some data values. And in addition, these agents could interact with other agents and offload tasks onto the other agents. In this way, we could distribute the execution of these workflows. One problem that we realized when we were executing, and this was the first approach that we had to program for the cloud edge IoT continuum, it was that we realized that, okay, we have a system that allows us to distribute the workload, but somehow we still need some event that is triggering that computation on every single node. And this is where we started to think about COLMENA, that is the new project that we started like 2 years ago. and based on swarm technologies. In COLMENA, the idea is that, as I said, we have the continuum, that you have several devices, a large amount of devices, and you want to execute a service on top of that. If you think of other examples of large systems with heterogeneous components, it's organic colonies. Organic colonies, at the end, it's a large organization, are large organizations, like, for instance, an ant farm, where you have a lot of individuals, each ant, and each member of this colony, at the end, it's an autonomous individual that it's taking its own decisions, being aware of its skills and capabilities, but still in a society with a context. And then every single member somehow contributes to the whole community by playing some specific roles or functionalities in the society. So bringing this idea of the organic colonies into the IT and the continuum domain, what we can have is that each service at the end, we can see it as a society, as a composition of several roles or functionalities that interact among them. And then each device can be an autonomous agent, an ant, that is aware of its own data processing, data storage, computation, and cyber-physical capabilities. This device has also to be aware of the context where it's executing. I mean, that might be the location, the ownership, or even the connectivity with other devices surrounding it. And finally, somehow, every device contributes to the service performance and to the service function by executing some specific roles of these services. I mean, the main difference between this centralized organization that I was telling at the beginning of the talk and what we propose in the COLMENA, it's the second fundamental idea, that's the freedom to fail. Instead of trying to find an optimal solution for the deployment, what we expect is that every single device takes its own decisions, tries to run it, and verifies if it's properly working or not. And for doing that, we leverage on some performance indicators. With these performance indicators, we can have performance indicators that indicate the needs of the system and the objective and relative performance when a device is playing a role. So every time that a device is checking these performance indicators, it can determine whether the system is performing well or not. If it's not performing well, it can start running some role and contribute to the functionality of the system. Otherwise, if we see a device is running a role, but it judges that it's not contributing to the whole system, then it can decide to stop a role. So at the end, we are building on the autonomy of each device to decide to avoid this problem of centralizing all the orchestration. What we are building is on the autonomy of each device to decide whether to contribute it in one way or another. So to better understand a little bit how COLMENA works, which is the programming model that we are proposing and the runtime system that supports it, I think that the best thing is to have a pilot use case where we can think about and see how COLMENA would fit in. And this pilot use case at the end, it's a video surveillance service that we are processing, that we aim to process all the images that are collected by cameras in the lobbies of the premises of some company to run some computer vision software and detect intruders that might be trying to get into the building. So at the end, we can think of some infrastructure like the one that is presented in this part of the slide, where we have several cameras, we have some edge servers that can process that have computing capability, large computing capabilities, and then we want the cameras that are in the lobbies to collect the images and so they can be processed. So at the end, as I said, what we are trying, I'm going to focus first on the programming model. So what we are trying to do is to declare one new service. So like that, with Python, we can declare a new service, video surveillance. We can declare two roles inside this service. One first role that would be collecting the images. We call it the sensing role. And then we have another role that is processing these images with the computer vision algorithms that we have. And this is how it would be done in the programming model. You would have the service and then the two roles declared as inner classes. An important thing that we said is that we want to collect images, we need to have some camera. And to process the images, probably if we have a GPU, the algorithms would run faster on those devices. So we can establish some requirements that one role needs to have in order, that one device needs to fulfill in order to run these roles. Like for instance, the sensing role requires a camera, you can establish like that I have here, we have requirements, we need a camera, or in the case of the processing, we said that we might need a GPU, so we can specify that decorating the role definition. In addition, we are not just having, as I said in the beginning, we are not just having the roles, but we also need some cooperation mechanism between these roles. In COLMENA, we foresee two different kinds of cooperation mechanisms. The first one is the channels that allow us to communicate from one role to another role. And the other one is data that allows us to maintain some shared data between the different devices, between the different roles, and that's it. In this case, the only thing that we need is a channel to send the images from those roles running the sensing role to those devices running the processing role. And we can specify that like this, by annotating the method with an add channel and the name of the channel that we will be using. Internally, inside the role, we also have a behavior function that is the one that is specifying which is the contribution or the functionality of that role. So in this case, we have two different kinds of roles, ones that are running persistently, like for instance, the ones that need to run on a camera need to constantly be getting the images from the camera and publishing them to the channel. And that's what we can see here. With this add persistent annotation, we have this constant execution of the behavior function where we are getting the images from the camera and we are publishing them through the pending images channel. On the other hand, we have also roles that they don't require to be constantly being executed, but they are reactive. That whenever we have an image being published onto the pending images channel, for instance, we need to execute that method to process the image. And this is the example that we have in the processing role. Whenever we are having an image from the pending images channel, then this behavior message will be executed, processing the image. Another important concept that we have is the context. At the beginning, I said that we want the processing role, the sensing role, to be executed only on those devices that are cameras, and those cameras that are in the lobby of the building. We don't care about other cameras that might be in a corridor or in some office space of the building. We are just interested in those cameras that are located in the lobbies. So for that, we have the context concept. The context represents at the end any circumstantial situation of one device. That could be, for instance, the location of one device regarding the premises of the company, or that could be, for instance, the continent, the country, the city where the device is located. That could be also the owner of the device, or any other thing that might be specific to the application. With this context at the end, for instance, what we said in this premises example of the company, we can have some devices that are in premise and some devices that are off premise. Of those devices that are in premise, at the end, you can have several buildings. You can have the headquarters, you can have the warehouse, you can have the store. So somehow what we are defining is a hierarchy, a tree of the context. And these trees can be as unbalanced as needed. For instance, as I said, we can have the in-premise, the off-premise. If the in-premises have buildings, then inside the buildings we can have different floors, or we cannot have floors, and then we have directly this lobby or whatever other room that might be on the description of of that context, of that situation, of that circumstance. So that is important because at the end, what it allows us is to contextualize every single device on this hierarchy, and not only on one hierarchy, but we can combine multiple hierarchies. So for instance, we can have a camera belonging to BSC that is located in the lobby of the headquarters, and then we can have some virtual machine, a processor 3, that it's deployed on an Amazon Web Services cloud that's off premises. So this allows us to define specific contexts and combine multiple context hierarchies on the selection of this of where the roles need to run. And that's a little bit what we are explaining here. In this picture, as you can see, we are defining one new context, that's the premises context, implemented in the premises class. This premises class is the one that I have here, where we are defining the whole structure of the context hierarchy. And then we have this locate method that allows the developer to locate that that device in this structure. So this is important because at the end, we can, using this context, we can limit, for instance, on one hand, where we want the roles to run. As I said, we are expecting only those cameras running in the lobby to be executed. And that's what we are stating here, that only those cameras running in the located in the lobby can run the role, the sensing role. This is also important because it allows us to define scopes for these cooperation mechanisms. In this example, we only have one single communication channel that allows that connects wherever devices are running the sensing role and the processing role throughout the system. But we could establish some communication channels that are specific for one building, for one floor, or one specific channel for those devices that are owned by BSC or that are, I don't know, in some specific city. So somehow it allows us to limit the cooperation mechanisms. So another thing that is important, and besides these communication channels, and the context and the roles, is how we define the metrics and the KPIs that will drive the system. In this case, what we are defining is just one processing time scope, one processing time metric that's custom for COLMENA provides some metrics by default, like for instance, the number of roles that are being played in one device. But we also allow the developer to specify some new metrics custom for their application. In this case, for instance, we want to know which is the processing time, the delay that we have to process one image. Because at the end, if we have 1 hour between when the image is captured and when the image is processed, it's useless as a security for a security system, because the intruder can already have left the building. So in this case, what we are defining here is that this service has one new metric, that's the processing time, and that will be published by the processing role. As we can see, we need to manage these metrics, so the sensing role gets the timestamp when the image is processed, and whenever the image has been already processed, we get the time when the image is captured, and when the image is processed, then we can compute the delay and publish the value for that metric. With these metrics, what we can define is the KPIs that will drive the system. That in this case, as you can see here, we have specified one KPI that says that the average processing time in the last 2 seconds should be less than 3 seconds. If this KPI is violated, then the system should react to it and start some role execution on other devices. If we see that the average processing time in the last 2 seconds it's less than 2 seconds, for instance, we can also react and stop some of the roles. This is one of the KPI, an example of a custom KPI, of a KPI using a custom metric. But as I said, we also have some KPI that are based on some metrics provided by COLMENA. And this is the case of non-players. In this case, we can see we are forcing the devices able to run the processing role to play the sensing role. So in this way, every single camera in the lobby will start processing the sensing role, will start running the sensing role, while the processing role at the end, it will depend on the workload of the system. So this is a little bit how it looks like, the example that I said before. As we said, we have the company premises. Every single device is running a COLMENA ant, the COLMENA agent. This COLMENA agent, at the end, the role abstraction, we have that the cameras are publishing the channels and the metrics. And then every single device is checking the quality of service, this average processing time in the last 2 seconds, to see if the system if the quality of service is violated or not. Depending on that, the system will decide if it's worth to stop running that role or if we should start, one of these idle devices should start running the role. So this is the part of the programming model. Now what we should see is which is the software stack that we have underneath in order to support that. So we have defined a software stack consistent on 4 layers. I mean, at the end, at the very bottom of the stack, we have the hardware node, or on its case, we could also think about virtual instances or virtual platforms. I mean, at the end, we have that that machine that at the end has access to some hardware, some network interfaces, some sensors, some cyber physical capabilities with sensors and actuators, some compute devices, and some data storage that are specific for that node, and that could be that could require have any interface to interact with it. So the first software layer that we have is what we call the ant handler, that at the end what it tries is to standardize the interactions between this ant or this agent, this device, and the hardware that has underneath. So we would have some communication controller, some controller for the smart system, some ant monitor that is providing metrics regarding the usage and capabilities of these network interfaces, sensors, and compute devices, some role optimizer that will optimize the execution of the roles to the specific hardware that we have in that device, and some configuration element to allow the owner of that device to specify how COLMENA can use that device. Once we have this standard API, this standard interface to interact with the device, what we build is the second layer, that's the swarm platform, where devices interact among them in order to fulfill this, to create a platform that is dynamic, elastic, and where we can run the different roles of the system. And for doing that, we have 3 big components. The first one is the context manager that will be checking persistently which are the self-awareness details regarding where I'm located in these context hierarchies that I'm running. But we also have this environment awareness that provides information regarding which are my closest neighbors, which is the rest of the system that I have, that we are running, the rest of the infrastructure that I have around. And we can have just information regarding which devices do I have around, or even some information regarding the latency of the connectivity or the latency for each of the network interfaces that we have around. So with this context manager, we provide information regarding the device, the contextual circumstances of the device. Then we also have all the part of the metrics. Okay, so all the metrics that we are receiving from the SLA, even those that are provided directly by COLMENA, or those that are defined by the application developer. We have a system that it's collecting all these metrics, aggregating them on a distributed system, and I'm verifying that we don't have violations in order to push some notifications that allow us to decide if we want some roles to stop or if there's a need to start a role. In order to decide which roles should be running on each device, we have this AI-driven role selector that is monitoring all the necessities of the system. It's monitoring which are the current usage of the device, and then decides which are the roles that should be started or should be stopped according to the preferences of the system. Finally, the last component that we have, this large component that we have here, is the sharing manager. With this sharing manager, at the end, it allows us to share software, and by software we mean the different container images or WASM containers that can be executed. So all the software can be shared across this software repository. We also envisage to have one data sharing software that allows us to keep data static and persistent even one device is lost, so it can be shared across the whole system. And finally, we have this compute sharing that allows us to share the computation, the workload of the system, in the same way that we were sharing the workload with the comms agents approach. And finally, on top of that, we have several tools that service developers or service providers can use in order to offer the service. So for the part of the service developer or service maintainer, we have this swarm programming model that is what I explained to you before. We have some role operation abstractions that simplify the development of the roles, like for instance, the implementation of the channels. And we envisage to have also swarm intelligence library implementing some swarm intelligence algorithms that can be used by the programmer. Once the programmer has finished creating this service, we expect the programmer, either the service developer, to provide a bundle to the service provider that would be the one that is actually instantiating the service on top of the underlying infrastructure of the swarm that we have. And for that, we have this service deployment tool that allows the service developer to either service provider to deploy that onto an infrastructure. And we are offering this service operational dashboard to see how the service is behaving and how the infrastructure is behaving. And finally, the top layer for this software stack is the service. I mean, the services developed by the user. So this is a little bit how we envisage the deployment of the COLMENA agent. So of the COLMENA platform. At the end, as I said, every single device, every single ANT has an instance of this COLMENA agent. This COLMENA agent has the components of the first layer running isolatedly in the device and providing some information to the upper layer, to the swarm platform layer, where the different components interact with the components in the other agents. Okay, once we start with this AI-driven role selector decides to start or stop a role, then we would start running this role as a different container, connecting these data abstractions, compute abstractions, with the sharing manager and the communication and smart system abstractions with the first layer. So somehow this is how we are deploying COLMENA as a service, as an agent, and how the different services running on top of COLMENA can be executed with this agent. So finally, to verify that everything is working and the different policies that we are developing, we have created a simulator that runs inside one node, and that we can specify the different situations, and that allows us to verify the different policies for this AI-driven role selector. In this case, we have developed 5 different. You can see here how the system, how this simulator verifies that the system is behaving when we're using a K-learning policy, this SARSA policy that are reinforcement learning techniques. We have some learning automata policy that you can see here, some rule-based policy, and then we have the random policies. So all these policies have been deployed in order to implement the AI-driven role selector. We can see here how the processing time behaves. We can see that most of the AI-based policies fulfill the requirement of being under 3 seconds, while the random policy, it's completely out of the, cannot control at all the service level agreement. And we can see that rule-based policies somehow are the ones that provide the best processing time. However, what we can see in the charts underneath is that the number of roles being executed. So we can see that the number of roles selected by the Q-learning or the AI-based policies, it's way closer to the actual needs of the system, while the rule-based tends to use more resources than needed, and that's why we have this better performance. So for that, we have, as I said, we have developed a simulator that allows us to verify the system, but we also have implemented a prototype of the COLMENA platform. Right now, what we are using is that these agents are implemented in Go. We are using the software Docker Hub as the software repository. However, we expect to update it to a peer-to-peer solution for the software repository. We are already, as I said, we are already implementing all this part of the metric publications with Zeno and the collection of the metrics with right now with Zeno, we are expecting to add also here Prometheus. And the role selector, I already explained that we are using the policies that are implemented by that were implemented by on the simulator. And then for the communication between the roles, what we are using is ZeroMQ. So this is an example of the results of running the pilot use case that I presented in an heterogeneous testbed that we were using only these 4 devices. We can see that when we start the service, we have 2 devices able to run the processing role and 1 single camera being on. So what we can see is that when we start the system, we have the camera is started in the camera. The sensing role starts on the camera, and for some reason, the AI role selector decides to start the processing role on both devices. After a while, since we can see here then the KPI, the evolution of the KPI, we can see that there's one of the devices that realizes that it's not needed for him to execute the process. So it stops running the processing role and the system continues working. At some point around second 40, a second camera is added to the system. And this second camera realizes that it needs to run the sensing role. It starts, and since it starts publishing messages, we can see that the service level, it's not working as expected. We are not meeting the requirements. So the second node realizes about the processor realizes about that and starts the processing role. After a while, we remove the second camera can be removed from the system, and since we remove the camera from the system, we see that the second device is no longer needed. And we can see here with a real example that this COLMENA platform can work at least in a small environment. So to conclude a little bit this presentation, what we have presented is that at the end, as a conclusion, we begin the talk saying that the programming and the orchestration of services in the Cloud Edge Continuum environments, it's a hard problem. I mean, both the programming and the orchestration itself. And COLMENA is presenting a holistic approach to solve both issues. On the programming model side, we are simplifying the development by leveraging on the concept of role with its abstractions that abstract away the programmer from the details of the infrastructure itself. And the COLMENA stack at the end, it's converting every single device into an autonomous agent that makes its own decisions regarding if it should start running a role or not, And in this way, we are fully decentralizing the management of the system. So currently, the current status of the project is, as I explained in the prototype, we have the simulator for testing the different decision-making policies that we have. And we have published also a first prototype in GitHub. You have here the web and the link to, if you want to check it. And finally, future work that we have. And as we said, I mean, some of the components right now, like for instance, the software repository, we're using a centralized entity like Docker Hub. Even if it's a public domain, public repository, we like to have a peer-to-peer solution in order to allow the system to work even when the cloud is not available. And the same for the data and compute sharing. We would like to implement it. We would also implement all the other models of the architectures that we haven't time yet to develop. And for that, we are cooperating with Evident to implement this quality of service monitoring with Prometheus and all these SLA management notification. And we also think about implementing other types of policies, not only those ones based in reinforced learning, but also some policies based in game theory, in auctions, in bio-inspired algorithms like swarm computing, and multi-agent reinforcement learning. And finally, this future work relates to the implementation of the COLMENA framework itself, but we are also looking at implementing a new use case in collaborations with the roots that at the end is trying to optimize and make more dynamic the operation of a power system network. So that's it. Thanks for your time and your interest. I'm leaving here some links. If you have any question, I mean, I think, Rosa, that we now are opening time for questions.
Yeah, we are perfect.
No time.
Thank you very much, Francesc. So is there any question in the audience? I don't see any in the Q&A channel. Feel free to post questions there. In the meanwhile, I wanted to ask you about the KPIs, no? Because so with the KPIs, you specify the reason why a new role can be spark or stop, no? But it seems a complex thing, no? Maybe you can describe what can be the challenges with the KPIs.
KPIs, I mean, at the end is what, I mean, somehow with the KPI, what we are dealing is with the agreement with what the developer expects to happen, what the developer wants the system to behave, and what is currently being offered. It's one way to compare, is the system behaving as the developer wants or not? And for that, that's why we need this KPI concept. At the end, we need some metrics to be published, and these metrics are objective. And you can see like, okay, I've processed an image or I haven't processed an image. And this is the only information that the system can automatically check for that. With the KPI at the end, we are just limiting a threshold of what is the desired level. So if I'm good having just 3 seconds delay, why do I need to have more roles running or not? More processing. In the case of the example, more processing roles running or on the other way around. If I'm just getting more performance that I don't need, like why is the point of having 10 processing roles if I just need to process the image in 3 seconds, and with one single device I could do that. So it's one way to control and adapt the execution of the system to what the developer thinks that should be, it's the correct way to do that. And that's, I mean, I think it's something that it was KPI and SLA management and QA management. It's something that we have done a lot of work in cloud environments for auto-scaling, for instance. What I think that these swarms bring into the picture now, it's the part of being contextualized. I mean, before we were expecting SLA systems to SLA service level agreements to be for the whole system, while maybe what we need now is to provide some KPIs that are specific to some situation. Like for instance, I want the processing image in this specific building to be, or in my building, to be less than 3 seconds. I don't know if that's, I mean, I think it's a challenge there to contextualize all the work that we did or that was done for this KPI and management of the system with the cloud. Now we have to find out a way to contextualize it and to bring it into the specific circumstances of the execution.
There is a question from the audience. It says, can you say something about the overhead of running COLMENA?
Not yet. I mean, we are, I mean, we are providing, what we are trying to build is a minimum valuable prototype. And we expect to at least to deliver the functionalities. We haven't measured, I mean, not even I mean, because at the end it depends a lot on, for instance, the specific policy that you need to execute the AI and the AI-driven role selector. Depending on the policy that you select, you may have more or less overhead in computing necessity in computing terms. So what we also expect is, okay, if you have a tiny device like an IoT camera, you may have a very, very simple policy to run there. While other devices in the system, like for instance, an edge server or a cloud VM, or even a whole Kubernetes cluster, then you may have more resources to run policies that are more complex. So in this case, if you are running the simple policy, you will have a lower overhead on the IoT device, while if you run on the Kubernetes, you can have a higher overhead, but just because you can afford it. So, but to the question of did you measure the overhead? Not yet.
Not yet.
No, because I mean, as I said, we are aiming to build first the functionality, and when we have this functionality, then we're gonna focus on the performance of the system and optimizing the system.
Okay, thank you. Any other question from the audience? Please feel free to ask. Another concept that is very interesting is the concept of context that you have in COLMENA. And I also saw that this was mentioned in the HiPEAC vision, no? And in this case, it was referred by the special web, I think, and they were mentioned like this. But in this case, I think is a little bit different because my understanding is that this standard for the spatial web is mostly related to web services, and this I think is more related to the devices themselves, no, to the context of the devices, no. What are the challenges on describing or noticing this context somehow?
I mean, for me, I mean, with the context, I think that as I presented it, we are following this hierarchical vision of the context, and I think it's the way to work. I mean, we have examples like, for instance, in geofences that are being used for service discovery, and I think that the challenge is not the definition of the context itself, but using this context. Like, for instance, what I said before, like, how can I describe the scope of sharing a data object, or which is the scope where a communication channel, which is the scope of the communication channel, which devices should receive the messages and which devices not. I mean, I think that most of the technologies that we have for submitting messages are based on the topic. It's, for instance, MQTT or things like that. You are publishing into a topic and then you subscribe into a topic. But it's not just subscribing into that topic. We have to add this context to the definition. So you will subscribe to a specific topic in a specific context, and you will receive the messages in that area. I think that the biggest challenge regarding this scope and this context management, it's not on the definition of the context, but on how we can specify all the possibilities that may arise for sharing an object. For instance, I want to share an object between all the lobbies, only between the lobbies. I don't want it to share it with other devices in other rooms, just in the lobbies. Or I want to specify it to be shared inside the building, across the whole building. Creating some kind of syntax that allows us to specify this, let's say, querying language, I think it's one of the biggest problems, because you can do it in several ways, but I think it's one of the biggest challenges, and I wouldn't know. Right now I presented it like this with star/lobby, but maybe there's other more complex situations that cannot be expressed with this typical regular expression syntax. So I think that there's a lot of work to do in this kind of syntax, and there's a big challenge there.
Molt bé, thank you very much, Francesc. Very excellent. Mira, there is one from Alba. Alba Cañete is asking, hi, Francesc, great job. I'd like to know if COLMENA will be able to be executed in any containerization technology. Thanks.
Yeah, that's the idea. As I said before, the agents are already running in Docker, and this Docker, it's what we are using to deploy the different containers of the roles. So at the end, containerization, it's part of the COLMENA philosophy, of the basements of COLMENA. Regarding running COLMENA in, I don't know, if you in a Kubernetes cluster, for instance, you have two ways to do that. One, it's exposing the whole cluster and running, as I said, it as the whole cluster as an autonomous agent, and that the COLMENA logic decides which are the roles that should be executed inside that cluster, or you could have, that's what I would do, or you could have a COLMENA deployment inside the cluster. But we foresee to use both. To use both, to use COLMENA on both situations. I think that it's more interesting for scalability to include the whole Kubernetes or any other compatible technology like K3s, to include that as an agent. The answer is yes.
Thank you.